So my name is Danny Flynn. I am the team lead slash project manager for the RockSat-X at Virginia Tech team. I'm a senior, a first semester senior, I guess, I graduate in fall. And I think we have quite a unique presentation for you this afternoon. So what we're going to be doing is giving you an overview of our team, our mission, but then also what we're going to do after that is instead of kind of giving you a broad technical overview of everything, we're going to dive deep into 3 subsystems for both of our missions. So we'll get into that. Right, there's our title. Your speakers this afternoon are myself. Eric Williams is our mechanical lead, who will be talking a little bit at the end. Jacob Girolamo is our electrical lead, who's also presenting on a subsystem. Danny Stover and Ben Piddlepow are also presenting on subsystems this afternoon. So I think as I just mentioned, we're going to do a team overview, a mission overview. After that, I'll stop talking. I hand it over to Danny to talk, I'll hand it over to Ben to talk about a star tracker / sensors subsystem for one of our missions. I'll hand it over to Danny to talk about some flight computer software, and then Jacob will wrap it up with an RF front end design. Okay. All right, so the RockSat program. This program's been around for about 10 years, maybe a little bit longer than that. The reason we say pushing the RockSat concept to new extremes with a capital X here is because this was actually predated by two other programs, RockSat-C and the Rock-On workshop. So RockSat-C is a similar program run by the Colorado Space Grant Consortium, where students are given a canister in a similar modular configuration to what we do to launch aboard a sounding rocket. And then the Rock-On workshop, both of these fly out of Wallops Flight Facility. And with the Rock-On workshop, students are given the opportunity to learn how to design a sounding rocket payload in about a week. So the X program came along, and Virginia Tech has been a part of it pretty much since its inception. We've flown almost every year, with the exception of, I think, like 2018, maybe one other year before that. We've consistently been able to make it past the down select and get an experiment flying every year. All right. So what the mission profile actually looks like is really interesting. So we're up there for a total mission time of about 10 minutes. Starting with launch, we typically fly it on a 2-stage sounding rocket. It's typically a Terrier improved Malamute, which you can actually see on this slide. This is our launch in the summer of 2021. Just as liftoff is happening. So we get up there. Our apogee is about 150 to 170 kilometers, depending on the conditions. And we're in the space environment for a little while. We get fully exposed to the vacuum. We have the opportunity to deploy things out of the rocket. We have the opportunity to, really just be out there for a couple of minutes. And then, of course, we re-enter the atmosphere, and we have chutes to fly, and we splash down in the Atlantic Ocean, some miles off the coast of the eastern United States. Right, that's it for the slide. Couple pictures here I'll get to in a second. What the program looks like, going even further into that, we have a design review cycle that lasts the entirety of the school year. So we start off in about August, and we start brainstorming ideas for what we might want to do, and it's completely open-ended. We can do essentially any project that we want to, provided we follow the rules that Wallops in Colorado set for us. So things like that might cause hazards to engineers when they're working on integrating rocket are probably not going to be allowed. Things like pressure vessels are typically not allowed, but you can work to get approval for this kind of stuff if the experiment does require something like that. So we start with brainstorming. We present a conceptual design review, typically in about early October. We work through a preliminary design review in November, and then the fall semester gets rounded out with a critical design review. They're, typically they get pretty long. 99% system definition is what we're looking for. And what we're looking for with that is to prove to Wallops and Colorado that the design is mature enough to move into the manufacturing phase. So provided we make it past that review, which I'm very proud to announce that Virginia Tech's team has done that this year. We're set to fly 2 experiments that we're going to talk about. Right we get past that, we spend all the spring working on manufacturing and testing from the subsystem level all the way up through integrated subsystem testing and culminating in a full mission simulation, and then handing it off to Wallops. So the pictures on this slide, just to give you a better visual idea of what we're working with, that's the rocket on the left, and then on the right, we're describing the setup that Wallops gives us to work with from like a physical perspective. So each of these deck plate sections is what we call them, is either half-sized or full-size, with a half-size being, about 12 inches in diameter, 6 inches tall, and a weight limit of 15 pounds, up it to a full size, and everything doubles except for the width, of course. So we have, again, about 12-inch diameter to work with. We have 30 pounds of weight we can put on there, and it's about 10 inches tall. So surrounded by this deck plate that the Wallops in Colorado give us is this longeron structure that everything's mounted into when it's assembled on the rocket over the summer. And this year, what we're doing is we treated both of our experiments as kind of separate entities, and they are being treated as 2 independent half payloads. Right. We are a very student-led engineering effort. Of course, we do have mentors and subject matter experts that I'll talk about in a second and are really invaluable to the team. But the student involvement is, we're right now a team of about 25. We're definitely one of the smaller design teams, which, that kind of happened by coincidence, but also going through the years, we kind of like to keep it this way because everyone on the team, whether you're a freshman or a senior, really gets to drill down and have a really big impact over what's going to happen. There are some downsides to that, such as if people leave, it can be sometimes hard to pick up that work. But overall, we found that it's worked for us. This year, our budget is exceeding $35,000. So what goes into that? The launch fees are $24,000, so about 2/3 of our budget. And then other things are like travel to Wallops, parts, of course, manufacturing things can get quite expensive, et cetera. Like I mentioned earlier, the team's been around for about 10 years. And something that's really awesome is we recently, within the past couple of years, got a permanent lab space in the Advanced Engineering Design Lab, which I'll show you a picture of in a second. And it's our 2nd year in that facility now. This is our organization chart for right now. So our leadership structure is somewhat limited. It's kind of 3 of us doing the bulk of the managerial aspects of the team. So I'm a project manager. I handle everything funding wise, logistics wise, planning wise, et cetera. And then we split kind of into 2 sub teams where Eric Williams over here is our mechanical sub team lead, and Jacob DeGirolamo is our electrical sub-team lead. They're in charge of kind of the engineering effort and making it actually happen. So while Jacob might be in charge of something like the electrical systems engineering and keeping track of our block diagram for all of our experiments, Eric is more in charge of physical constraints, making sure we're staying within the limitations of the program, making sure everyone's getting their CAD together, things like that. To help them out, this year we started kind of a new role. That's this lead or chief engineer position. So on the electrical side, we have 2 members, Charlie K and Danny S, who are our lead electrical engineers, and they're kind of taking on additional responsibilities for each of the 2 projects we're working on. And then same thing on the mechanical side. We just have one right now, Ben Masters, who's in the room with me right here, is our lead mechanical engineer and is primarily responsible for the direction finding experiment that we're doing. Okay. This is a picture of our lab space. So we're permanently in here. This is the RockSat-X in the Advanced Engineering Design Lab. We have this big, maybe half the size of this conference room table in the middle, where right now it looks very different from this picture. It's very clean right now. There's a lot of stuff going on in the lab right now. Got a nice banner. We just got these shelves for storage. So I really like to thank Bob Schoner and Dewey Spangler for getting this set up for us. And actually, while I'm talking about that, I really want to thank, back to the previous slide, all of our subject matter experts and mentors and our team advisor. for all the help that they give us and allowing us to seek out help when we're stuck on things. So going from right to left, I guess, we have Dr. Kevin Chimpaw as our team advisor, Zach Lepke and Kevin Stern from Space at BT / the Hume Center help out with a lot of RF related things. Dr. Robert Smith is from the Calhoun Discovery Program and the Boeing Company, and he's been very helpful with some mentoring in the past. Randy Spicer and Ben Heckman are from Northrop Grumman Space Systems, and we meet with them on a regular basis to keep them in the loop with what we're doing. And then this year, Dr. Greg Earl, who is in the call, he has helped us out with this Langmuir Probe experiment that we're doing, and I'll get to in a second. All right. I'm not going to go into this that much because I'm kind of going over my planned time already for my section, but these are some past payloads we've done. From left to right, we have, this is actually the first 3D printer to actively 3D print while on a launch vehicle. We have some RF experiments, putting software-defined radios up into space. That happened kind of in the 2016 to 2018 era. So the middle top and the bottom right. On the top right, that's an experiment where we got the local high schools involved and actually did some like high school student experiment deployables. And then in the bottom on the center, this is our most recent mission. It's a deployable CubeSat form factor solar panel array. So that fits into 1U CubeSat size, and it was a deployable solar panel array. And we just flew that last summer after developing it for 2 years because one of our launches got canceled with the whole global scenario. All right, I'll go real quick through the mission overview to give you a top level picture of what we're working on right now, and then I'm going to hand it off to the subsystem designers to talk about their parts of the project in detail. All right, our first mission, this was started in the 2020 to 2021 school year. It's a direction finding system to estimate the angle arrival of ADS-B signals. And essentially what that means is ADS-B signals are like aircraft position packets. They're broadcast by aircraft, and they contain information like the latitude, longitude, altitude, time stamp on them. And what we're doing is we looked at this and we wanted to do some sort of like phased array or beamforming like project. So with the help of some of our SMEs, we turned it into this project where we're doing direction finding of these signals. And they're a really good candidate because in addition to being able to do this angle of arrival estimate as the mission, we can actually compare it to like a ground truth by decoding the packets themselves. And that gives us a really good baseline to compare to. Our systems engineering process starts with generating mission objectives and success criteria, and requirements flow down happens from there. So listed on the right are the success criteria for this mission. We're looking at recovering just raw recorded RF data during this mission, and then in the post-processing of the mission, doing the actual beamforming, doing the actual AOA estimate, and doing the comparison. Mechanical design of this mission. So, of course, very unique deployer requirements. We have to get these antennas spaced out at a uniform separation of half a wavelength at 1090 megahertz. You do the math, it's something like 13 centimeters. Very unique electronics enclosure. Of course, we have to protect our mission and our electronics not only from the hazards of space, but also from after splashdown, we're soaking in the ocean for quite a while. And as we've learned in the past couple of years, it tends to take on water. So unique electronics box. There's been some manufacturing troubles. We're trying to cast it out of aluminum and kind of make our own custom lid and bolt it on there to protect everything. Electrical design. This is our block diagram. So I could talk about this for 30 minutes, but in essence, we have an RF front end and antenna system recording RF data from there. Those flow into software-defined radios. We have a flight computer that consists of an Odroid single board computer and an MSP 432 to handle all of the data storage. We have some kind of housekeeping sensors to help us debug if something goes wrong. And we have a DC-DC power conversion system that interfaces with a rocket. So we're provided 28 volts and some current limits. And from there, it's our responsibility to step that down to whatever we need. We also can interface with the rocket for some telemetry downlink, and that's shown on the left of this diagram. So later in the presentation, we're going to be focusing on two of these systems. specifically the RF front end and antenna systems. Jacob's going to be talking about those, and then the flight computer, mainly the software. Danny is going to be talking about that aspect of the project. Some pictures of our hardware, PCB stack, put in this form factor, of course, to avoid vibrational concerns. This kind of approach has evolved even more going to the next mission that I'm about to introduce. Antennas on the top right with a bias keyboard to power the amplifiers, which are actually outside the box. Jacob will talk more about that. Bottom right, picture of our sensors board, trying to program the microcontroller. All right, the second experiment. This was started in 2021 and is going through the 2022 year. We're working on a Langmuir Probe mission to characterize the plasma of the lower ionosphere. So with this, we're looking at measuring characteristics of the plasma, including the electron temperature, the ion and electron density, and then what we're going to be doing is comparing that to the existing IRI model for the atmosphere. All right, I'm going to try to wrap up within 1 minute so we have time for everyone else. Our success criteria there. Electrical design here, a little bit more simple than the ADS-B mission. We really wanted that because we were unsure of whether 2 missions at the same time was going to be feasible for our team. Everyone has done a really great job so far. I'm very proud. I'm confident that this is all going to work in time. And we're going to be focusing on the sensors and kind of a bonus star tracker system that we put in. Ben Kittlecow will be talking about that. I'm very impressed with that system. Ben, I think, is only a freshman, right? Yeah. So you'll hear more from him in a few minutes. Mechanical design, we're going pretty far out from the rocket. I really don't have time to get into the constraints on this, but pictures are right here. And then this is some pictures from the IRI model. So our expected results are going to be these characteristics versus altitude, essentially. And we can compare them with these, which we generated from that model. All right. So with that, we'll get into the star tracker first, and we should have about 10 to 15 minutes to go through those slides. So Ben, if you want to come up here and take it away.
So yeah, this is the star tracker component of the Langmuir Probe or Langmuir experiment sensor subsystem. So specifically within the sensor subsystem, the green box shows where the star camera is. So at the beginning of the year, we were tasked with, or me and my teammate Kevin, who were both working on the sensors system. We're tasked with making housekeeping sensors that would work for the following year, maybe build some flight heritage. So the reason why we added the star camera, although it's not, I'm going to explain this later why, but it's not quite important for this flight, for the Langmuir Probe experiment, but we are adding that for future missions that may require the star camera. Yeah, the purpose of the star tracker is to track and identify stars in field of view, and it computes attitude, which is orientation relative to a J2000 reference frame. So that's essentially time from midnight, January 1st, 2000, and specifically, attitude and position are what are required to describe an object's placement in space. So you can see in the 3 pictures kind of how attitude changes. You can see the blue vector in the left image pointing kind of more towards the top right. And then as thrust is applied to the spacecraft, the vector changes its orientation. And that's the change in attitude that we're trying to figure out with the star camera. So there's 3 operating modes that the star tracker is going to have. First is initialization mode, to check if the star tracker is working, to verify parameters. And then there's the first mode, initial acquisition mode, which will identify kind of where in the sky we're looking at first, so we know which stars are which, and then we track those stars. Since after initial acquisition, we know exactly which stars we're looking at. So the actual star catalog, so how this works is we compare what the camera sees to a catalog of star positions that was, for this mission, we're using the Hipparco star catalog. So we're going to compare whatever the camera sees to this catalog and see where certain matches are. And I'll talk a little bit how we do those matches. So the catalog lists position, brightness, other properties of 118,200 stars. So that's a lot of stars. The catalog was published in 1997. There's a picture of the actual spacecraft on the bottom right. And other catalogs have been made and are available at the USNO. And the bottom image is a graph of the position of the stars with right ascension, declination, made from the entire catalog. So that's what it looks like. So in flight, we're not going to use the entire catalog because, as I said, there's over 100,000 stars. So we're going to generate a catalog using a subset of the Parker's catalog. And how we're going to do that is by figuring out the parameters of the camera to generate this catalog. So if the camera can only see down to magnitude 5 stars, for example, then we only need to use stars in the catalog that are down to magnitude 5. And as a quick note, magnitude is kind of opposite. So the higher the number, the dimmer the stars. So for this, I also made some statistics. So on the left, there's all the stars mapped to a sphere in the catalog, and all the red dots are the centers of field of view. So if you imagine kind of you're around Earth, you're looking out into the sky, into the stars. Each red dot is where the camera is pointing at in the sky. So we can determine based on lens parameters how big the field of view is going to be. On the right, you can see the projection of that field of view onto the two-dimensional right ascension declination graph. Once again, all the red dots are the center of the field of view. But here, what I did was, because the plan is not to use the entire detector, use a small portion of it, the green stars is that smaller portion within the detector. So although the camera can see all the red stars, we're only going to use a smaller portion just because of certain artifacts that come out of using the entire detector. So there are other star trackers that are similar size to what we need, but they aren't particularly financially feasible. So for example, we got the CubeSpace star tracker on the top right, accuracy of 95.2 arc seconds. And the cost isn't listed, so that could only mean it's expensive. Usually what that means. And then below that, another smaller one. Once again, sizes are listed, so these are relatively small. They can be used for CubeSat satellites. The accuracy is 2 arc seconds, although I don't think that's true. I don't think they're actually adding in certain error sources. But the cost, as you can see, is $40,000 to $50,000. There's no way we could ever afford that. So, and yeah, any high performance star tracker would have a larger C swap or cost, size, weight, and power. So designing our own star tracker will lower the cost, although the performance might not be the best. I believe for any application, the performance we need doesn't necessarily need to be super high accurate. So the actual components that we're going to use, and I'm developing currently with, is the Raspberry Pi and the OB9281 camera. So this camera detector is a global shutter detector. It's a CMOS APS detector, and we chose this one specifically because it can directly interface with the Raspberry Pi, and it was relatively cheap. And the pixel size is 3 by 3 micrometers. and the actual Star Tracker microcomputer that will be doing all the computations necessary. It will be the Raspberry Pi 02. I'm going to be using the OpenCV Python library, and the maximum frame rate I was able to get was 233 frames per second at 1280 by 800 resolution. But in flight, we're probably going to have a frame rate around 1 frame per second to about 10. Reason being is that initial acquisition requires some time to figure out which part of the sky we're looking at. And the actual tracking can speed that up a little bit, but still we need to kind of track it where stars leave the field of view. So we need to keep doing that star catalog comparison. So the total cost is about $70 plus cost of the lens. And so for this star tracker, I've had to do a lot of different, I've had to learn a lot of different aspects of engineering, kind of being a systems engineer. So the biggest part of this is photonics. There's a lot of different factors I've had to take into consideration. So for the lens choice, so as I said, I don't actually know the cost of the lens yet, probably around $90. But I haven't chosen a lens because the lens depends on the parameters of the detector. The manufacturer did not give us all of the information necessary for the detector, so I've had to measure those specific parameters. I believe Dr. Herrera is in the Zoom call currently, so he is helping me out with those measurements. So very much thank you for that. So we've been developing a test plan, so hopefully we can get those parameters and finally pick a lens. Another kind of aspect, spot size on the actual detector kind of ties into the lens. Depending on the lens, the spot size on the actual detector changes. This Q factor, which is essentially resolution ratio of the lens and detector. So how good the lens is versus the detector. And ideally that should be about 1 and 1.5. There's detector sensitivity. Once again, that is one of the main parameters that needs to be measured to choose the lens. And then start brightness and start and color spectrum. So I actually need to figure out the percent stars the star tracker is likely to see, and calculate the color spectrum for that. See if the camera can actually detect down to those brightnesses. And yeah, so there is a trade-off between field of view and signal to noise ratio. So really all of this is kind of a balancing act. And it really brought, if I determine the detector's parameters, a lot of this can be figured out. And just as a quick note at the bottom, there's a diffraction point spread function. And the image on the right is what a finite aperture lens would see. So if you had a perfect lens, no matter what, that is what the detector would see, just because of certain distortion effects. So other aspects of engineering I've had to deal with is embedded electronics. So not only do I have to work on the star tracker algorithms, I also have to figure out how I'm going to communicate the star tracker system with the rest of the sensor subsystem. So I've had to deal with communication bus interfaces. You can see a simulation of SPI data transaction on the right. And as far as software, like I said, I've had to develop algorithms. Thus far, it's been in a MATLAB, just developing both the algorithms and test code, for like the field of view test. And on the Raspberry Pi, I'll be using Python to write those algorithms. And all the different software aspects are listed there. Also, communication with host and camera, I have to physically write the software to enable that. We're planning on using a real-time operating system. And I've also had to use real-time debugging using the STM32 JTAG debugger, the logic analyzer, and protocol analyzer. And as far as mechanical, I've also had to think about how the star tracker interacts with the environment. So there's the sun, which is very hot, which will cause the star tracker to get very hot. So I've had to take that into consideration. Certain angles that the actual camera can face on the payload have to be taken into consideration. And also have to think about where the moon, the earth, and the sun are during flight, so that when we do put this on, it's not facing towards the earth or any other bright object. And there's also vibration, shake and bake, camera degradation. So just verifying that the whole system will function in the flight environment. Okay, so here's some images of my algorithm. So far, I've been able to make the initial acquisition software. So on the starting from the left, top left, there's simulated focal plane containing, I believe, 13 stars. And then I filter that out to black and white, filter that with a Gaussian filter, and then convert that. Actually, moving back, that's not black and white, that's gray. And now for the last one, I convert that to black and white. And then moving to the right, the white dots are actually generated by the code, so it knows exactly where those stars are in terms of pixels. And then on the far right, there's the algorithm can cut out those stars into chips. So you can see an example of a dim star and a bright star. It's easy to see in the bright star, there's actually a small white dot in the middle, and that indicates the centroid or the center of that star. So we know exactly where that is in the field of view. And just as a note, the blue kind of background is noise due to dark current, thermal noise, and photon noise. So I've simulated that as well as this. And those are my references. And yeah, that's it. Anyone has any questions I can answer right now? Otherwise, I believe we have time at the end for questions.
Cool. Thank you, Ben. Yeah, so I guess we might go a little bit past 3, so we can give everyone time to talk about everything, all the great things they've been working on. But thank you so much, Ben. And we're going to move to our next subsystem now. So, all right, I think next up, Danny Stover is going to talk about the flight software and flight computer for the ADS-B mission. So, do you need the screen right now, or are you going to do this first?
I'll share.
You'll share? Okay, I'm going to give Danny the screen.
All right. So, yeah, my name is Danny Stover. I'm one of the lead electrical engineers for the 2020-2021 ADS-B packet payload. And I'm going to be talking about flight software engineering, specifically for a space mission. So basically, I've been working on the flight computer, which is the computer that manages the sensors, deploying the deployer using a motor. And so all of these things kind of have to happen at the same time. So I'm going to go through basically like what I've been considering while writing the flight software for the flight computer, specifically for RockSat, which is a very different environment than what you're doing in school classes, you know, where you're developing code for a computer and not like an onboard computer that's going to be in space. So the first challenge that I've run into is that you have to have several processes running in parallel. And so just like I said, there's sensors, there's a motor, there's telemetry, and there's a camera. So the solution to that is designing code that runs on multiple threads. You can see there's 4 threads we have, which I'll be going into later. The second challenge has been knowing what's going on at each point in flight. Obviously, the microcontroller is not in space right now, so I have to kind of think about what will be going on and how do I log this while the microcontroller is in flight without even being able to test that. So, we can't view that data, and we have to rely on the data to confirm that events even happen, such as the deployer being deployed. So the solution to that is timestamping data and logging messages, which you can see in the code here. The third challenge has been debugging issues in flight. So this is pretty interesting. Thing that not a lot of people think about is that, we're flying this thing, we won't be able to touch it. If one thing goes wrong, that one issue can't cause the entire software to just stop or malfunction. You actually have to, it's pretty challenging to write software where if one thing breaks, you have to continue debugging it. And so the solution to that is basically having a separate thread that handles all the debugging. So instead of stopping the software, you kind of hand it off to the thread that says like, okay, let's try to fix this while the rest of it's still working. And one thing to note is that you do want to prioritize mission critical elements. So for example, if the motor is broken, you want to try to fix that as much as possible, as opposed to maybe like the camera, which is a backup system. And then the last challenge, of course, there's many others, but the last one I'll talk about is that microcontrollers are not easy to manage. This has been, especially when the team has never really used a certain microcontroller before. So we're using an MSP 432, and there's low RAM compared to your own laptop. You have to use specialized development environments and languages, and then writing the software for it's actually very different. And the solution to that is just being patient, which has been hard. So I'm just going to go into the hardware. We have an inertial measurement unit, a barometer, an accelerometer, and an SD card reader. So these are the sensors. We have the microcontroller, which you can see the development board for that microcontroller on the right. And then we have a stepper motor and a camera. And the software tools we're using are an IDE called Energia, which is basically Arduino, but ported for the MSP 432. And I'll go into why I use that later. And then C++ with the Arduino library. So considering all those challenges, this is kind of the design of the software that we came up with. So there's the 4 threads. There's a thread for data collection and storage. There's a thread for debugging any issues, a thread for the motor, and a thread for the camera. And instead of just talking about it, I actually wanted to quickly just show what the software looks like right now. So I have a software tour. So this is VS Code. I love VS Code. It's great. But on the left, you can see all the files that are actually going to be running on the MSP 432 in flight. So we have the main, I guess, script here. It's called Sensor Flight Controller Main. That includes, all the libraries we want to use. I do want to highlight, I guess, like the reason I'm showing a software tour as well is I want to highlight good coding practice. So this isn't software that's just like a 600-line file where everything's being run sequentially. There are C++ libraries that are written basically for each sensor. Like the IMU has its own library file, SD card has its own library file, barometer has its own, and then the main script kind of includes them all. And instead of being super long, the main file is actually less than 100 lines, which is great. So essentially, Arduino already organizes like a setup in a loop. So a flight controller or flight computer, of course, is going to be kind of an event-driven loop. So you want it to loop forever and ever until you don't want it to. So it starts whenever the whole system's powered up. That's just what happens. The code starts. So you have to be able to handle when do you actually start collecting data. And so we have like 180 seconds from power on to liftoff. So we have to make sure that we only start collecting data really when we want to. So we set up everything, basically initializing all the sensors. And like I said, if there's anything that goes wrong with initializing, we have variables that are basically sent to the second thread, which is the debug thread. So the debug thread essentially just says, okay, if something's not initialized, try to initialize it. Now the problem is you don't want to do that continuously because that will suck up processing power. So basically I just check it every 3 seconds or so, kind of an arbitrary, number, but you kind of have to have that delay time in between. And then in addition to the sensor data collection and the debugging thread, there's also a motor thread. So this one basically just triggers on a certain timer event. So after a certain time, seconds after launch, we want to deploy the antennas. So, there's just a, deploy the motor. And then after more time, we want to retract the motor. And then we basically want to just stop this thread. So just delay it forever. We don't need to use it anymore. And something to mention, I guess, is in order to run this software, we have to use the IDE called Energia, which is this. It looks like the Arduino IDE, but it's red. That's literally all it is. Essentially, it's amazing. This is an open source project that was built to just be able to write Arduino code for the MSP432. So I can just upload it. It's not magical. I've had to debug several issues with it. There's a lot of code that isn't written or completely written. So there's kind of some sacrifices we've made. The other alternative to using this would have been to write bare bones C code for all of the sensors, and did not want to do that. So we went to another option. But yeah, all this software is the same thing you just saw, and I have to compile it for the board using Energia. And the way this works basically is it actually handles a lot of the operating system by itself. So I don't actually have to write any operating system code. It does use the TI operating system, the RTOS for the MSP432, but it's super simple. You actually just have to make a new tab and make a setup and a loop function, and then that'll create a whole new thread. So that's very nice. And yeah, I guess that's kind of the software we have. It's been really awesome to work on it, and very, it's just like a totally new experience compared to what I've done before and I've learned in classes. So I'll hand it off to Jacob next.
That's awesome. Let's go back to my laptop. You need yours. I need to use mine. Okay. So I'm Jacob, I'm the electrical team lead, and I worked on the ADSB RF front end for the ADSB direction finder project. So first, a little bit about ADSB. I don't want to go too in depth because we're short on time, but okay, is the mic down here? Yeah, it's down there. Okay. So the ADSB packet, there's a long packet and a short packet, but we're looking for the long packets. And these long packets contain information that we need for this mission, including the altitude, latitude, and longitude. And these are a pulse position modulated RF signal. And so to receive that, we have to have a front end in front of our SDR. And that comes with a lot of design constraints. So the first one is that we have to produce some gain in this front end. So the ADSB can be decoded with about a signal to noise ratio of 15 dB or higher. And so we use the freeze noise equation and then set up a link budget to estimate the reception range of our front end. And in doing so, we receive this plot here. And anywhere within the 15 dB ring of that, we should be able to receive from our payload. And you can see we actually receive most of the East Coast, which includes a lot of major airports. We should be able to get plenty of test data from here. The next major consideration was size. So you can see the deployer is retracted in this configuration in this picture. And these antenna elements have to be less than 1 centimeter in width. The antennas, which aren't shown in this picture, have to be able to fold up so they can fit within our keep out zone. And then another consideration that we had was that we have to have filtering and amplification external of the payload as close to the antenna elements as we can, so we minimize the loss of the coax. And these three are the main considerations driving the design. So I'm going to talk about a couple different things. First, we'll start with antennas. Like I said, the main constraint is that they have to be pretty thin and they have to fold up. So we're using tape measures, which will fold up between some metal parts. And then as the deployer deploys, they will passively just fold back down and become the antenna elements.
So we made some test boards with some balance and produced a couple of these tape measure antennas that are flexible and full. And then here are the S11 plots for those antennas. So on the left, we have a Smith chart, and you can see our impedance is right on 50 ohms, which is what we're hoping for. And that's after the balance. So it's a 75 ohm to 50 ohm balance. So we can convert the 72 ohm antenna impedance to the 50 ohm impedance that we're looking for on the receiver. And then we have a return loss of negative 35 dB, which is great. That means it's a fairly efficient antenna, even though it's pretty small, holds up everything still. The next thing to design was the front end. So this includes two main components. It's a bandpass filter focused on 1090 megahertz, which is the center of frequency for ADS-B, and then a PGA 103 amplifier, which is a wideband low noise amplifier. Designing a test board for that circuit and characterizing it. This is the ST1 plot, so it's a plot of the RF through the amplifier. You can see we have this giant hump in the middle. That's the bandpass filter. And you can also see our amplification is about 12 dB over the input amplitude, which is great. So that means that it's acting as we intended, except for the SWR. So looking at the S11 Smith chart, we can see this red marker right on the frequency of interest for our front end. And it's at about 75 ohms. So digging into the data sheet of the bandpass filter a little bit, the bandpass filter is actually a 75 ohm component marketed as a 50 ohm component with an SWR or standing wave ratio of 1.8 to 1. So to remedy this and to minimize the loss because of this, we decided to use a 75 ohm to 75 ohm balun instead of the 75 to 50 ohm. So we'll still have a little bit of loss between the bandpass filter and the amplifier, but we won't have that loss between the balun and the bandpass filter. The next issue is power, because these antenna elements are external to the power supply which is within the box. So we're using a bias T and injecting the 5 volts over the coax cable. So we have an LC network on both sides, and then we can actually inject DC in between those two. So in the actual schematic, that looks like this. We have a 4-channel bias T board, which is inside the box. That's that top schematic. In the lower schematic, you can see this new section on the end, which is a LC network, which will actually take the 5 volts off of the RF line and feed it back into the amplifier. So now to put it all together, here's a block diagram with the 4 channels. So we have the 4 dipole antennas, the 4 front ends, which are the balun, bandpass, and amplifier. And then we have the bias T board, and then those 4 channels all go to the radios. And we have a 12-volt linear supply going from our mission power supply to our bias T board. Here are the PCBs designed for the project. So on the left, you can see the bias T board. There's 4 channels with some SMA connectors, and also a 7805 linear regulator. So we take the 12 volts in from the linear supply and the mission power supply and regulate that down to 5 volts for the amplifiers. And then on the right over here, on the top, we have the top board of the front end where the balun is, and then the 2 antenna elements. You can see some on the sides there, connected by those 4 larger holes. And then on the lower board, we have the SMA connector, the amplifier, the bandpass filter, and the bias T network. So that looks like this in the CAD. It's pretty small. It's about 1 centimeter wide, and the top board is about 7 centimeters long. And the whole thing is about 1 centimeter tall, plus the SMA connection screws on the bottom. Here are the actual 4 boards. You can see the bottom one has the antenna elements on them made out of an actual tape measure. And then you can see on the right over there, the manufactured bias T internal board. So far, we've been able to do a single channel and a 4-channel test with these, and we've actually been able to receive ADS-B signals through the front end, which is great. It means that it's working well. And then our next thing to do is we're going to do a 4-channel test outside of our lab. Our lab is a nice big metal box. So we were able to receive ADS-B through it, but not very much. So we're actually going to do our 4-channel test outside again to receive data that we can then post-process as if it were flight data, and then begin developing our post-processing scripts. So any questions? Or are we going to say questions for Dan?
I guess it's a general question.
Yeah, we can have Eric do the conclusion, and then we'll get into questions for everyone. And I can check the chat as well.
Sounds good.
Yeah, I pulled it up on my.
Yeah. We want to swap back to my laptop. Thank you, Jacob.
Yep, thank you.
Really awesome.
Where you want.
Sharing it.
Yeah.
All right, and that's the end of the bulk of the presentation. So Eric has a little bit of a conclusion, and then we'll get into questions.
Okay, yes. So as you can see, we did do over the course of this presentation, discuss a significant portion of the electrical systems here. There is also supporting it, all of this, plenty of mechanical work. However, the good portion of that stuff is still under development, since it requires significantly more prototyping that cannot be done using virtual simulations on computers. Thank you to all of our sponsors for this cycle, especially the Aerospace and Engineering Department and Northrop Grumman and Boeing, who have provided significant assistance, in addition to all these other fine folks, including LIDOS, the Student Engineering Council, and Lockheed Martin.
And of course, Space VT.
And yes, of course, Space at VT has provided both a little bit of material support, but also plenty of advice and guidance towards the creation of our payloads. I think with that, questions. If you're not, if you don't want to speak up, you can place them in the chat. We have the chat box open here, so we can ask the people who are in there. Okay. That's just Professor Earl.
Thank you, Dr. Earl. Awesome. Yeah. Definitely a lot of testing going on there soon. A lot of stuff's been ordered, so I'm sure they'll run into trouble, and we'll we know who to call when that happens. So in the next couple.
I'm particularly interested there. I do have to drop off, but I am particularly interested on whether you guys have decided to go with a linear or a log amplifier on that. And also what your approach is to, if you did go the log amp route, what's the approach to making sure that you don't have a negative, problem when the current goes negative as you sweep through the, the range of voltages on the probe. So, we don't have to talk about that right now, but if your team has answers to that, I'd like to know what your approach is, or if you have questions about that, feel free to get in touch and we can talk about it in more detail.
All right. Thank you, Dr. Earl.
All right. Thanks, everybody.
Okay. Additional comments? You have some stuff? Yeah, go for it.
This is also incredibly exciting for me. Thank you so much for doing this. I just read this stuff day and night. So I've been looking for avenues to get into space at VT. I'm a graduate student at this.
Awesome.
First of all, I wanted to know what kind of so you're using solid rocket motor as your
Yes.
propulsion for your propulsion.
Yeah. Yes.
What Eric has.
Yes.
What class of motor are you using?
So this is a full-scale NASA sounding rocket. We're buying space on it. The particular model, if you want to look it up, is called the Terrier Improved Malamute.
Okay.
That is the particular one. It's two-stage, and the best way to describe it is two military surface-to-air missiles stacked on top of each other with that R stuff on top. So
Analogy.
yeah, no, it's literally one of the engines is off of Patriot, like extra engines from the Patriot program.
What your structure materials? What is it made of?
Okay, yes, so the actual base plate that we're all building on is aluminum, as well as the majority of our structural elements. We also are increasingly using 3D printed elements, but obviously the temperatures we're dealing with, you can't do anything normal. So the majority of our 3D print elements are in this material called Ultem, which you can either get 3D printed or just in a resin block that you can machine out. We usually go for the 3D printed method just because of how precise a lot of our components are. We are also looking to do a large chunk. Some of the inside the electronics box doesn't have to have the same thermal loading constraints. So those can be more like
in the region of like ABS plastic. Other than that, stainless steel bolts just to keep everything locked down tight.
Big hunk of metal for ballast if we're underweight.
Yes, and yeah, that is actually really interesting. We've done in the past done really well on keeping the mass down of all of our components. So we've actually had to put on ballast, which also helps us meet the constraint of getting the center of mass on the center line of the rocket, which is very important for them because the way this whole system operates, it is spin stabilized on launch. So it is very important for us to not do anything to upset that radial symmetry.
So what kind of constraints do they give you? Weight constraint and space?
We have a whole like tens of pages long user's guide that has all the constraints, all the program requirements, all of the mechanical requirements, all of the electrical interfacing.
Yeah, it is publicly available.
Yeah.
So if you stay after this, I can navigate you to that website if you want to take a look at it.
Do you guys use any method of thermal management on board or something?
Yeah, definitely. So a lot of our electrical components generate a lot of heat, namely the power converters. We typically do go with switch converters so we can get something like 70 to 90% efficiency instead of like 20 or 40 as with a linear converter. But even then, we have to heat sink all this stuff. And of course, we're in space. Pretty much the only way to dissipate heat is through radiation. So to be honest, we just heat sink everything to the box.
And since
see a piece of metal right there, so just thermally bind all of our electrical components that we can to that.
And yeah, the box and that is also in contact with the deck plate, which is then in contact with the rest of the rocket. So there is space for the heat to go, especially over the short time frame that we're operating under. But yeah, mostly the electronics box itself is a good fit of the heat sink.
And coming to the avionics part, that you guys don't have any method to visualize the telemetry dashboard or something because you don't have any idea what is going on in the space. Only when you get the data back, you know when the event happened.
Yes. Sorry, you go, Jacob.
Yeah, so we don't have any live telemetry during the mission. All of it is recorded on the rocket and then brought back down. So NASA takes 1/2 of it and they report it and then they will give it to us. And that's a pretty high likelihood that we'll get that back. Ours is like if our box floods or anything in the ocean, we likely won't get it back. So we rely on both. We're done saying.
Yeah. Also for uploading the code, the firmware on board, you said you were using ID Energia MP, right? There is Energia MP.
Yes.
Energia MP. Have you looked into and you use VS Code for all your C++ development?
Yeah,
Have
we're
you
all
looked into Platform IO?
Platform IO?
Platform IO.
No, I've never heard of
I
it.
think you should look into that. Like I'm trying to develop my own flight software and I've been using Platform IO ID. That's the extension within VS Code involved.
Okay.
Yeah.
There's an online question, a question about 3D printed processes. So yeah, to expand on that, we also have our own 3D printer in the lab at AEDL. That it is mostly printing in PLA. So obviously that is nowhere near the proper temperature threshold for flight components, but it is great for initial prototypes or just whipping something up. Yeah, you can see it in the back on top of the red toolbox. And your other question here from Sean is, when's the launch?
Yeah, so the exact date, I don't have it memorized, but it's towards the beginning of August. It's like 9th, maybe 10th. I don't think the exact date's set yet, but beginning of August.
Yeah, so right before it begins. And
Yes, it is a ride share with several other universities. So how the RockSat program works is there's 5 full-sized sections, and we compete for spots. So it was overbooked this year, and fortunately, we made it past down select and got both of our spots on the rocket.
Yeah, and the down select is on the criteria of how mature the design is and how far along you are, as well as their confidence in you being able to execute on what you're planning on doing.
Right. Awesome question. Thank you.
Anyone else in the chat or online? It's like going once, going twice. Okay, I think we're gonna wrap it up there. Thank you everyone for coming online and in person. Yes, we will see you at the next time, or someone on this team will be here in future to share where we get to. And we are on Twitter and Instagram, and we'll be posting updates to those accounts as we reach milestones up until launch, and then what we're up to in the future.
Thanks everyone for coming.